So we're going to go ahead and look at the pH scale. So before we go ahead and look at calculations with pH and pOH, we're going to look at the significant figure rules associated with pH and OH. So the number of decimal places in the pH that you've been given or that you calculate is going to equal the number of sig figs in the concentration of your H3O plus concentration value. So example, in this case my pH has 2 decimal places, so my H3O plus should have had 2 sig figs. Okay, if this had 3 sig figs, then I would have 3 decimal places in my pH. Okay, so pretty straightforward significant figures, but basically make sure that you're comfortable with these 2 rules. So let's go ahead and look at pH and pOH. Okay, so basically pH and pOH, they're related to each other, and we'll discuss how. But basically the pH scale allows us to express the concentration of our hydronium ion or H plus ion, however you want to look at it, with numbers that are pretty easy to understand. So the scale that we typically learn is from 0 to 14, although you can have values higher than 14 and values lower than 0. So please be aware of those. It is possible. Okay, so basically in order to calculate pH, basically what we do is we take the negative log of our H3O plus concentration. And in order to calculate pOH, we take the negative log of our OH minus concentration. So knowing our hydronium concentration, knowing our hydroxide ion concentration, those both allow us to calculate our pH and our pOH. Now, these two are related, the pH and the pOH are related by this scale of 14. So basically the sum of your pH and your pOH is always going to equal 14. So basically these 3 equations really allow the relationship to basically be found, or basically allow you to interrelate and intercalculate to find out concentrations of each of the individual species. So understand, in this class you're not going to be looking for, oh, just give me the simple pH. You may be asked, given the pH, and you might be asked about hydroxide ion concentration. And basically these calculations obviously all need to be able to be done, so understanding and knowing each of these equations is important. Now, I know you guys probably are already familiar with this, but remember that a pH of 7 is considered neutral. Anything greater than 7 is going to be basic. Anything less than 7 is going to be acidic. Another thing I want to mention before we move on is basically how do we figure out our concentration values from our pH or our pOH. Okay, and basically guys, if I want to know my concentration of my H3O plus and I know my pH, basically if I just do 10 to the negative pH, that's going to give me my hydronium ion concentration. In that same thought process, if I want to know my hydroxide ion concentration and I know my pOH, if I take 10 to the negative pOH, that will also give me my hydroxide ion concentration. So basically, if you want to be familiar with all these equations, you should be able to comfortably calculate what you need. Okay, so they've asked us here in these 2 examples. Okay, so this first one, they've asked us told us the H3O plus concentration of an acidic solution is 3.5 times 10 to the negative 3. What is the pH and what is the pOH? Okay, so obviously we have been given the concentration of H3O plus. So the calculation for pH is actually quite straightforward. We're just going to take the negative log of the concentration of H3O plus. So in this case, 3.5 times 10 to the negative 3rd. Okay, if we go ahead and calculate that out, we're going to end up with 2.455, okay? But remember, we're going to only have 2 places past that decimal because we have 2 sig figs in our concentration value. Okay, so really 2.46 would probably be the more appropriate value. Okay, so this is the pH calculation. Now, they want us to calculate pOH. All right, so in order to calculate pOH, there's actually multiple ways that we could actually approach this problem, but since we just looked at these equations, okay, we can go ahead and utilize this relationship to calculate our pOH. Okay, so 2.46 plus pOH is going to equal 14. Okay, so basically 14 minus 2.46. pOH is going to therefore be equal to 11.54. Okay, so as I said, there are other ways to approach this. You could use KW calculations. to figure out your concentration of your OH minus ions, okay? Because remember, we're assuming that we're at 25 degrees C. Okay, you could subsequently plug in what you know, which is your H plus concentration. You know your Kw constant, so you could solve for OH minus, take the negative log of your OH minus, and subsequently get your POH. So I would suggest you try to solve this on your own, make sure that that's actually true. And as you can see, there's multiple ways to, you'll be able to see is that there's multiple ways to approach these problems. So let's go ahead and let's look at this next one, okay? So in this situation, since I've given the hydronium ion concentration straight away, and they don't ask for pH, they ask for POH, I'm going to go ahead and use the Kw in order to calculate my OH minus concentration, because that's what they want. Okay, so 1.0 times 10 to the negative 14th is going to be equal to 2.3 times 10 to the negative 3rd, because that's the concentration of my H plus, and then my OH minus. Okay, so OH minus concentration is going to be equal to the 1.0 times 10 to the negative 14 divided by 2.3 times 10 to the negative 3rd. And that's going to give us 4.34 times 10 to the negative 12. Okay, so that's going to be our concentration of our hydroxide ion. And if we go ahead and take the negative log of our hydroxide ion concentration, okay, this is going to give us our POH, which is going to be equal to 11.36. Okay. And basically that should correspond to the appropriate pH, if we wanted to go ahead and basically reverse this process and check it using the pH plus POH equals 14 equation. So obviously all these relationships allow us to find out some important information. Okay, so let's go ahead and look at calculating the pH of strong acid solutions. Okay, so the first thing we want to do is make sure that we're paying attention to the acid-base equilibria. We want to focus on the solution components and the chemistry that's happening. So basically, in this situation, say what species are present in a 1 molar solution of HCl? Okay, so you should look at this and you should say, all right, I have HCl. HCl is one of the strong acids that you need to have memorized, and we know that with strong acids, they ionize almost 100%. Okay, so the reality of it is I don't really have very much HCl in solution, but instead have H plus and Cl minus ions in solution. Okay, so first step, focus on the solution components and what chemistry is actually happening. So understanding and differentiating between strong acids and strong bases is going to be very important. Okay, the next step, you want to determine which components are the major species and which ones can actually be ignored. Okay, so what species are present in that 1 molar HCl solution? So remember, we talked about the fact that we had H plus and Cl minus, and of course, you know, H2O is going to be present because it's a solution, it's a 1 molar solution. Okay, obviously there's not going to be any hydroxide ion because it's an acidic solution. There's a strong acid present, so there shouldn't be anything there. Okay, so we know that our sources of H plus are going to be from the HCl, and of course there could always be a little bit of H plus present from the autoionization of water. Now, if the concentration of HA or of that acid is less than 1.0 times 10 to the negative 7, we actually need to consider this. But in this case, obviously we're looking at a 1 molar solution of HCl. Okay, so this doesn't really apply in this situation. But later on we'll look at situations in which it does. So let's go ahead and let's look at this. All right, so HNO3, guys, HNO3 is which acid? Okay, so you should have said nitric acid. Nitric acid is one of the strong acids. Okay, so what's going to happen with nitric acid in solution is it's going to ionize into H plus and NO3. Okay, so remember, we need to, NO3 minus. We need to consider, obviously, what's going to happen with this species in solution, right? So HNO3 is a strong acid. It's going to ionize completely into these two ions. Now remember, I'm going to have this ion and this ion present, and of course I'm going to have H2O because this is a solution of acid, right? Now we need to consider, is H2O going to be a contributing factor to the amount of H plus present? Because remember, they want us to calculate pH, and pH is going to obviously be calculated by taking the negative log of our H plus or H3O plus concentration, right? So in this case, our concentration of HNO3 is very much so larger than the 1.0 times 10 to the negative 7 molar, so we don't need to consider our H2O concentration as being a contributing factor to our H plus. All right, so what we can do is if I know the concentration of my strong acid, I'm subsequently going to know the concentration of my H plus and any other contributing ions. So in this case, whenever you're dealing with a strong acid, right, if you know that concentration of that acid, right, so in this case HNO3, okay, you also know the concentration of your H plus ion. Okay, remember, we're not considering anything coming from that H2O molecule. So in order to calculate pH, I'm just going to take the negative log of the concentration. All right, and this is going to give me a pH equal to 1.00. Okay, so fairly acidic. It's a pretty acidic solution. Okay, so guys, with strong acids, obviously the ionization is considered to be 100%, and only if the concentration is very, very low, so lower than 1.0 times 10 to the negative 7 molar, do we need to consider any protons or any H plus produced from the autoionization of water. Okay, so let's go ahead and look at the calculation for the pH of a strong base. So before we go ahead and look at calculations, let's actually talk about what are the strong bases that you guys should be familiar with. So basically, strong bases, any of the hydroxides from groups 1A and 2A in the periodic table are going to fall into that category. So sodium hydroxide, potassium hydroxide, both examples of strong bases that you guys are relatively familiar with, or at least should be. Okay, so group 1A hydroxides, they're going to completely disassociate and they're going to produce your metal ion and a hydroxide ion. Group 2A hydroxides, on the other hand, they are strong dibasic acids. Notice they're dibasic because they have two hydroxide ions attached, but they don't dissolve very well in water, and so obviously they're not very soluble, so that's one of their issues. However, they obviously are a strong base because when they do dissolve, they produce that hydroxide. Okay, now they're actually commonly used in antacids because what ends up happening is that you don't have a complete dissolution or complete ionization. You actually basically have to have the presence of an acid in order to get them to break apart. And basically by the time that's the case, you produce water from that neutralization process that will occur. So we can go ahead and look at magnesium hydroxide's usage in the stomach. So as we know, the stomach contains hydrochloric acid. And basically, when we add the magnesium hydroxide, we know that magnesium hydroxide doesn't dissolve very well in water. But when we add it to the acidic solution that's present in the belly, basically this magnesium hydroxide is able to ionize into these hydroxide ions. And what ends up happening is that instead of a big old buildup of hydroxide occurring in our stomach and us, becoming very, very ill, what ends up happening is that the HCl reacts with the magnesium, or with the hydroxide ions from the magnesium hydroxide. That produces this magnesium chloride and water, and you get this neutralization process. So basically it calms down the stomach, and you feel a little bit better. So an example of a strong base being utilized to balance the pH in someone's belly is seen here. Now, the reason why we show these examples or we look at this is that we typically think of strong acids and bases as ionizing completely and things of that sort. And although that's true, there are situations where you have a strong acid, or in this case, a strong base that's not going to ionize in water, but will ionize completely in something like an acid, and subsequently give you the same results. So please be cognizant of that. Okay, so some more questions. Can you have a base without OH minus? If you don't have a hydroxide ion, can it still be a base? And the answer to that is yes. As long as you have a substance that can accept a proton, basically it's going to produce OH minus ions when it's put in water. So the example of NH3, as we've talked about, this is a weak base. If we put that in water, it's going to accept the protons from H2O because H2O is going to act as the acid, Okay, our NH3 is going to act as the base. There's going to be the transfer here. You're going to produce the conjugate acid and the conjugate base. And in this case, the conjugate base is a hydroxide ion. Okay, so in order to do this, though, you're going to need an unshared pair of electrons to form that bond with an H+. Okay, and in these situations, guys, you're usually going to have weak bases. So basically NH3 and any of its amine family members are typically going to be weak bases. So you can totally have a base that's without a hydroxide. They're going to produce hydroxide in solution, but please understand that they're usually going to be weak bases. So now let's go ahead and let's look at the calculating of the pH of strong bases. Okay, so in the case that we see here, we've been asked to calculate the pH of a 0.028 molar solution of NaOH. Okay, so I've been given a solution of NaOH. Notice, NaOH, the strong base, it's going to ionize completely into the following. Okay, so we're going to assume that since it's a strong base, it ionizes completely. Okay, and we know that the concentration of our NaOH and our concentration of our OH minus is going to be in a 1-to-1 situation because we understand that those are the ions that it breaks into. So if I know the concentration of my NaOH, I know the concentration of my OH minus. Okay, so these are equal to one another, right? Okay. And so those equal 0.28 molar. Okay, now guys, notice they want us to calculate pH. Okay, so pH is the negative log of H+ ions or H3O+ ions. There are no hydronium or H+ ions in this situation. So really what we need to do first is calculate our pOH and then calculate pH. So if I take the negative log of my hydroxide ions, okay, that's going to be equal to my pOH. Okay, so if I go ahead and plug that in my calculator, that's going to give us 1.552 as my pOH. Now remember, pH plus pOH equals 14. Okay, so I know my pOH, so 14 minus 1.552 is going to give me my pH. So if I go ahead and plug that in the calculator, that's going to give me a pH equal to 12.447. Okay, and that corresponds to a basic solution. Okay, now if we go ahead and look at this other example with calcium hydroxide, okay, same idea. Calcium hydroxide, though, when it breaks up, it gives us the following. Okay, so notice there is not a 1-to-1 relationship between my strong base and my hydroxide ion. All right, so because the relationship is not 1-to-1, you're going to have to use stoichiometry here in order to figure out your concentration of your hydroxide ion. So 0011 calcium hydroxide. Okay, there's a 2-to-1 relationship, so we use our stoich here. And that's subsequently going to give me my concentration of my OH minus, which is going to be, 0.0022 molar. Okay, so if I take the negative log of this, that's going to give me my pOOH. Okay, and that's going to give us 2.65 as our pOH, and they want pH, so 14 minus 2.65 is going to give us our pH, which is going to be equal to, that's going to give us 11.34 as our pH.